in chemistry, we use a lot of models. Now, it's important to remember that a model will have many of the features of whatever it is we're trying to represent, and it's those features that help us to understand the thing better. It will not have all the features. It's not an exact picture of the thing, but it does help us to get a grip on the concept and help us to understand the thing a little better. So what we're going to look at today is something called particulate diagrams. And these are little pictures that we draw to help emphasize certain features of different substances. For example, solids, liquids, gases, solids that are dissolved in water, that sort of thing. So let's look at, first of all, solids. We want to represent the fact that in a solid, the individual particles are very close together. And not only that, but in most solids, and we would call these crystalline solids, in most solids, these particles are not just close together, but they're also very orderly in nice little rows or some kind of pattern. So we will represent that with just a little grid. So this is what it might look like. Now, some kinds of solids are not in a nice square formation like that. Sometimes you get solids that take other formations, and they might have crystals that look like hexagons and things like that. But just to get the idea of the fact that the solid particles would be very close together and very orderly, we'd probably draw it something like this. Now, if we knew what solid we were talking about, we would draw the symbol for those elements inside the circles. So let's say that I have a chunk of solid sulfur. Some forms of sulfur, most forms of sulfur, if they're pure, will be yellow. So you might have a yellow powder. I actually have a jar of this stuff back in the chemical supply room. So I'll have this jar of yellow powder, and if I were to think really small about what it looks like to get way down small and look at the individual atoms, it would look something like this. So I'll put S in the middle of all the atoms, because S is the chemical symbol for sulfur. Now I'll do another one just to show that sometimes we have substances that are not pure elements. Sometimes we have substances that are, for example, maybe an ionic compound. So we might have something like sodium chloride. In that case, I'll have two circles, and one would be labeled sodium and one would be labeled chloride. And draw them a little bigger so I have room to write my symbols in it. Now, sodium chloride happens to be an ionic compound, and that means that the individual particles are not just plain atoms, they're ions. Ions mean that these are particles that have either lost some electrons or gained some electrons so that they now have a charge. At this point in your chemical career, assuming that you're watching this in September, you would not be expected to know which atoms are likely to form ions or even what kind of ions they would form. But I will put in the correct symbol just because I should do that. So let's say that this would be a sodium ion, so that would be Na for sodium with a plus sign, and this might be a chloride ion, so Cl for chloride with a minus sign. And then I would continue that with sodiums and chlorides and sodiums. And I'll put a chloride down here because a positive and a negative are likely to be next to each other. And I will start with sodium and chloride and sodium and chloride and so forth. And you can see how that's going to work. Now in the drawing it looks all two-dimensional just because it's kind of hard to draw three-dimensional, but we have to remember in our minds that this is really a three-dimensional grid. So if we had a solid, the thing that this diagram shows us is that the particles would be very close together, actually touching each other, and they are nice and orderly, nice little grid. So let's think about liquid and how that's different from a solid. And what we want to show here are two things. First of all, that the particles are still very close together. It's important to understand that in a liquid we still have particles that are touching each other. They're very close together. It's still what we call a condensed state of matter, and it's still fairly dense. Not much different in density from the solid usually. The difference is, though, that now the particles are free to move around each other. They're no longer going to be locked in this orderly grid, but they're more likely to be kind of chaotic and disorderly. So if I wanted to show sulfur that was melting, I might show it, see if I can do this and make it look disorderly. Not that easy to make it look disorderly, actually. But the idea is that it's not locked in a nice tight grid, and these particles would actually be moving past each other, rolling around each other, and not fixed in place. If we were to think about how these particles move, all they do is sit there and just vibrate. If we were to think how these particles move, they're doing this rolling around each other, and that's why liquids can pour. And again, if you knew what it was, you would put the element symbol in there. Now a gas, something totally different. As you know, gases are not very dense, meaning they don't have a lot of matter squished into a small space. Their matter is very spread out. And the gas particles are very far apart, and the spaces between them are very large compared to the size of the particle. So sulfur gas would not be very likely to happen. I guess we could make sulfur gas if we got it hot enough. So let's pick something that's more likely to be a gas, maybe oxygen. We're familiar with oxygen. So oxygen comes as O2 molecules. So we would have an oxygen here and an oxygen there stuck together, and I'll label each one of those O. And then maybe way over here we'd have another pair of atoms that are stuck together. That's what O2 means. And each one of those is an O. And we'll stick another one over here. And each one of those is an O. So maybe I'm going to draw a line here to show that that's still part of the gas. Maybe we could do nitrogen also. I'll erase my oxygen and do something different. Nitrogen also is what we call diatomic, meaning there's two atoms that are bonded together. So we'll do nitrogen gas, put an N there and an N there. Maybe another one over here, maybe another one way over here. So for you to represent a gas, the important part of that would be to make sure that you separate the molecules or the atoms from each other. Now if we had something like argon gas, that does not form diatomic molecules, that forms just individual atoms. And we might have just one circle here, and one here, and one here, and we could label those argon. So this is what we mean by a particulate diagram. And later in the year, we'll look at what happens when substances dissolve, and we'll learn to draw particulate diagrams for those as well. But this is as far as we need to go right now.